Hello, welcome to day 132. Before we get into 132, let me just review 131. Um, Lots of information on 131, which is why I made today kind of light. So, I did go over answers to everything. Here's a link, and exit questions are here, so take a look at those, please. Okay, day 132. So, efficiency. What is it? You should have a definition for that, and you should have thought about what it means for a car to be efficient. If you haven't, go ahead and pause now and then come back. Okay, so efficiency. Well, what's it mean to be efficient? Achieving maximum productivity with minimum wasted effort or expense. So there's lots of ways to do this. Right now, if you're organized, you're efficient with your time. You don't waste any. When we talk about car engines, well, so car engines, right here, here's a gas engine. This is efficiency. This is output and power here in megawatts. And over here is thermal efficiency. These are all heat engines. And a gas engine gets between 30 and 40% efficiency. The rest of that goes into waste. Mostly, well, think about it. What happens um, when you touch an engine? How does it feel? Hot, right? That's waste. Any unburnt fuel is also waste. So that's why there's things like catalytic converters and other things, other mechanisms that try to get all the energy out of these things. Okay, so that's our warm up. I wanted you to read about efficiency. That's on page 268. So that's right over here. And there's a few equations to use. One is the work output divided by the work input times 100 to get a percent. That's the efficiency. And basically, all that's saying is that whatever you put in divided by what you get out is the efficiency. So if all of the work that you did came out as work, then it'd be 100% efficient. When you use a bottle cap opener, it's pretty efficient. There's not much waste there. Um, and so pretty much all the effort that you're putting in is what you're going to get out when you open that cap. However, like we just said with the car engine, not the case. A lot of it turns into heat and other waste. Another way to calculate efficiency is by rearranging some of this stuff, and the book does a good job talking about that here. We can rewrite the efficiency equation in terms of mechanical advantage and ideal mechanical advantage. So if you've already calculated those things, you can use those to solve problems. And that becomes pretty handy when I ask you to solve or answer question 32 and then 25C, which is a follow-up from yesterday. So let's take a look at those. So over here is 32. It says, suppose you increase the efficiency of a simple machine. Do the mechanical advantage and ideal mechanical advantage increase, decrease, or remain the same? Let's go back and look at the formula. Oop, one too far. So if you, oh geez, now I forgot it. If you increase the efficiency, does that mean that this number here has to get bigger or smaller? Bigger. So that means this has to be larger, which means either the mechanical advantage has to be larger or the ideal mechanical advantage has to be smaller. One of those two things has to occur. Or they both could occur. All right, next question was 25C, calculate the efficiency of this. So this was a problem that we did yesterday, and I'll just go straight to the link from yesterday. Here it is, it's 25. We've got the ideal mechanical advantage here is 4. The mechanical advantage is 1.5. And so we can use those two to solve the problem. Let's go back to the formula. And we would divide 1.5 by 4, which is, I think, 1/6. So that's the deal there. Instructions for notebook check are here. Please let me know if you have any questions. And that's it. Have a great day.